Good morning, students. In the last topic, we were dealing with the formation of PN junction diode, and in that section we studied that after the diode has formed, the PN junction diode is always neutral. That means the number of positive charges is equal to number of negative charges in a diode. So the diode as a whole is neutral. And we studied about the barrier potential also. Barrier potential is defined as the potential difference which is created inside the depletion region, which prevents the further diffusion of electrons and holes. Today we are going to discuss how a diode can be connected in forward bias as well as in reverse bias. So you can connect the diode in two patterns. The first thing is forward bias and second thing is reverse bias. So let us see how this system works. Diode in forward bias. In forward bias, the P side of the diode is connected to the positive terminal of the battery, and N side of the diode is connected to the negative terminal of the battery. This type of biasing is called forward biasing. So we can say like this: the positive terminal of the battery is connected to the P region and negative terminal of the battery is connected to the N region. Then we can say the PN junction diode is in forward bias. So let us see what will happen when the diode is in forward bias. The holes in the P region are repelled by the positive terminal of the battery and they are moved towards the junction. Similarly, the electrons on the N side, they also will get repelled due to the negative terminal of the battery, and that electrons will move towards the junction. So as we increase the applied voltage slowly, we are increasing the voltage from 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, so on. So as we keep on increasing the applied voltage, the holes from the P side are repelled and moved towards the junction. Similarly, electrons from the N side will move towards the junction. As a result, what will happen to the depletion region? Initially, depletion region was having this much width, and as I increase the voltage, the width of the depletion region decreases. Okay, initially the width was this much, and after that the width will decrease. As the applied voltage keeps on increasing, the depletion region width will keep on decreasing, and at a certain point called threshold voltage, at that time the depletion region will become very thin, and at threshold voltage the depletion region will vanish. And soon after the depletion region vanishes, electrons from the N side will cross the junction and combine with the holes on the P side. Similarly, holes on the N side, holes on the P side will cross the junction and combines with the electrons on the N side. That means soon after the threshold voltage, electron hole recombination will take place, and as a result a high current will flow through the diode. So initially when I increase the voltage from 0.1 volt, 0.2 volt like that, there will not be any current. The forward current will be almost negligible or almost zero. But as the applied voltage increases, as I told, the width of the depletion region will decrease, and when it crosses the threshold voltage, then the depletion region is vanished and the barrier potential is overcome, and soon after overcoming the barrier potential, electron and hole recombination will take place and current will flow through the diode. So current flows through the diode, a very high current will flow through the diode only when the diode crosses the threshold voltage. So we have already studied in the last class, the barrier potential is 0.7 volt for silicon and 0.3 volt for germanium. So if I am using a silicon diode, soon after crossing the 0.7, that is considered as the threshold voltage here. So soon after crossing 0.7 volt, there will be a sudden rise in current. If you are using a germanium diode, then soon after crossing 0.3 volt, a very high current will form. Okay, so threshold voltage is actually related to the barrier potential. It is just opposite. If the barrier potential is in the reverse direction, the barrier potential will be in the reverse direction. You can look it here. So if this is 0.7 volt, the applied voltage is also 0.7 but in the opposite direction. Only then the barrier potential is overcome. You can look here and here. These two these two symbols of the battery are in the reverse order. And the forward current of the diode is of the order of milliampere. Okay, what we have discussed is what I am showing here. So you can copy this as notes. So the potential barrier, as we discussed, the potential barrier and width of the depletion region decrease. Therefore, large number of majority carrier will diffuse across the junction. Hole current and electronic current are in the same direction and they get added up. Once they cross the junction, the holes in the N region and electrons in the P region become the minority carriers of charge and constitute minority current. For each electron hole recombination, an electron from the negative terminal of the battery enters the N region and then drift towards the junction. In the P region, near the positive terminal of the battery, an electron breaks the covalent bond in the crystal and thus a hole is created. The hole drifts towards the junction and the electron enters the positive terminal of the battery. This is how the current is transmitting. We already told no, during the electron hole recombination, as a result of the recombination, forward current will take place. This is how the forward current is taking place. Now, the current in the external circuit is due to the movement of electrons, whereas the current in the P region is due to the movement of holes and the current in the N region is due to the movement of electrons. Because in the last class, in the last video you studied, for a P-type semiconductor, holes are the majority carriers, and for the N-type semiconductor, electrons are the majority carriers. That is the reason I told here, in the P region the current is due to the movement of holes and in the N region the current is due to the movement of electrons. If the applied voltage is increased, that means when it crosses the threshold voltage, large majority carriers will diffuse across the junction and a large current will flow, and that current is of the order of milliampere. This is what we have discussed. Okay, so write all these points in your notebook. Now let us move on to the next thing. The diode is in reverse bias. What is meant by reverse biasing? In reverse biasing, the positive terminal of the battery is connected to the N side, whereas the negative terminal of the battery is connected to the P side. It is exactly what we have done in forward bias. Okay, the positive terminal is connected to the N side, the negative terminal is connected to the P side. So when the diode is connected like this, what will happen? Just imagine what will happen. The reverse process of what we told just now will happen. Okay, so look at the figure. The positive charge holes are connected to the negative terminal. So what will happen? This negative potential will pull the holes backward. As a result, the holes will be attracted and moved backward. Similarly, this positive potential will attract the electrons on the n side. As a result, the electron from here will move towards that side. Then what will happen? Initially, depletion region was having this much width. The width of this depletion region increases. Okay, the width of earlier the width was only till here. The width of the depletion region will increase because the holes are pulled by the negative potential, whereas the electrons from here are pulled by the positive potential. So the barrier potential also increases. The width of the depletion region increases, and as a result, what will happen? No current will flow through the diode. So we will conclude like this: when the diode is in reverse bias, very high resistance will be there on the diode, and as a result, no current will flow through the diode. Diode will not conduct when it is reverse bias. That is the first step. Now, think about the minority carriers. So before telling about the minority carriers, you can just write this. As we discussed, the holes in the P region are attracted by the negative terminal of the battery, and the free electrons are attracted by the positive terminal of the battery. As a result, the majority carriers are pulled away from the junction. The potential barrier and width of the depletion region will increase, and as a result, what will happen? It becomes more difficult for the majority carriers to diffuse across the junction. As a result, no diffusion current will take place. That means diode will not conduct. Okay, diode will not conduct. Now, there are certain other aspects also. We were talking about the majority carriers, and due to the majority carriers, there will not be any current formed. That is what we have studied. There is no current formed due to the majority carriers. But think about the minority carriers. Which are the minority carriers on the P side? P side we studied majority carriers are holes. So obviously minority carriers are electrons, right? Similarly, on the N side, minority carriers are holes. So you just think about those things from the diagram. In the P side, here minority carriers are electrons, and here minority carriers are holes. Those electrons, listen to me carefully, those electrons, those minority carrier electrons here will be repelled by the negative terminal. It will be repelled by the negative potential, and they can drift towards this, drift towards the N side. Similarly, which are the minority carriers on the N side? Holes, right? So those minority carrier holes, they are repelled due to the positive potential. Okay, so those minority carrier holes will be drifted towards the P side. So drifting of the minority carriers take place. That means when the diode is in reverse bias, the minority carriers will drift across the junction. As a result of the drifting of the minority carriers, there is a very small current which is of the order of microampere will flow through the diode, and that current is called reverse saturation current. So at a given temperature, the rate of generation of minority carriers is constant. So the resulting current is also constant irrespective of the applied voltage. The resulting current is also constant irrespective of the applied voltage. That means even if I increase the voltage, the minority carrier's minority current, the reverse current will not increase. It is of the order of microampere and it remains constant. Do you know why? Because the amount of minority carrier is constant. It is not changing. That is what I told here. At a given temperature, the rate of generation of minority carriers is constant. Number of minority carrier is constant. As a result, the reverse saturation current is also constant. It does not depend on the applied voltage. That is why we call reverse saturation current. Now, since the minority carrier number is very small, this current is also very small. It is of the order of 10 raised to minus 9 ampere in silicon diode and 10 raised to minus 6 ampere in germanium diode. That is why I told it is of the order of microampere. For silicon diode, it is of the order of nanoampere, that much small. So in effect, we can say the diode will not conduct, because in the forward biasing, the current is of the order of milliampere. Microampere means 1 by 1000th of that. Nanoampere means 1 by 1000th of microampere. So in both the case, the current is extremely small. So we can just say the diode will conduct only when it is forward bias and does not conduct when it is reverse bias. Okay. Now, the reverse bias PN junction diode has an effective capacitance called transition or depletion capacitance. The P and N regions act as the plates of the capacitor and the depletion region act as the dielectric medium. So, in reverse bias, PN junction diode has an effective capacitance, a very small capacitance will be generated here, which is called the depletion capacitance or the transition capacitance. Okay, so this is all about the reverse saturation current. For any diode, there is a limit that it can withstand with the reverse biasing voltage. You already know in your household devices also, if I increase the voltage beyond a certain limit, what will happen? The device will break. Some device, if it is a bulb, it will get fused. If it is a fan, its coil will get burned off. Like that, all the device will fail if the current is more than a required limit. Here also, in diode also, the same thing happens. In reverse bias, the reverse saturation current will remain constant for a wide range of voltage. Say for example, we are talking about 0.1, 0.2, 0.7, such kind of volt. These diodes in reverse bias, they can withstand with like about 20 volt or something like that. If the voltage is increased beyond that, the diode will break. So just before the breaking down of the diode, the minority carriers number will keep on increasing to a very high extent, which result in a high reverse current, and after that the diode will break. This voltage is called breakdown voltage of a diode or a Zener voltage. So the largest voltage that a diode can withstand, the largest reverse voltage that a diode can withstand is called the breakdown voltage. I marked it as VB, breakdown voltage. Soon after reaching the breakdown voltage, the minority carrier number will keep on increasing numerously, and as a result the reverse saturation current will increase very high, the reverse current will increase very high, and after that the diode fails to work. The diode will break. That is why it is called breakdown voltage, and it is also called as Zener voltage. Okay, so here I am just showing two graphs in one plot itself, two graphs in one plot itself, The first one is when the diode is forward bias, and second one is when the diode is reverse bias. So if they ask you to draw the circuit diagram when the diode is forward bias and reverse bias, you don't have to draw the diagram which I have shown in the beginning. That diagram is only for explanation purposes. What I mean is, you don't have to draw this diagram in your exam paper. This is only for the explanation purpose. You draw this diagram. When the diode is in forward bias, you draw this diagram, and when the diode is in reverse bias, draw this diagram. Okay, this is what should come in the exam paper. Okay, so VI characteristics of diode or diode characteristics. VI means voltage current characteristics. So I will take the voltage in the x axis and I will take the current in the y axis. As we discussed already, initially there won't be, when the diode is in forward bias, initially there won't be any current, and soon after it reaches the knee voltage or threshold voltage. Soon after it reaches the knee voltage or threshold voltage, there will be a rise in the current. That is why the graph goes like this. Think about the second graph. Second graph is this portion. Here you can see there is a small current which is called a reverse saturation current. Don't draw this pink line along the x axis. What you have to do is, you just draw the line somewhere below the x axis. That means the line should come like this, and then it is constant, and then it rises down. Okay. So this voltage is called breakdown voltage. So a current comes like this, which is of the order of microampere, and thereafter it increases. The diode is having two type of resistance: static resistance or DC resistance, and next one is called dynamic resistance or AC resistance. DC resistance is same as R is equal to V by I, whereas AC resistance or dynamic resistance, we will take delta V by delta I. What is delta V? V2 minus V1. And what is delta I? I2 minus I1. So if I ask you to find the dynamic resistance, you will take any 2 points here, any 2 points on the graph, and then you will take I2 and I1, V2 and V1. Then V2 minus V1 by I2 minus I1 will give the answer. Okay. So if they ask you to draw the VI characteristic of diode, this should be the graph you have to draw, and make sure that this pink line should come below the y axis. It should not pass along the y axis, it should come below the y axis, and then it comes like this. Okay. So that's all for this video. Thank you.